Hello, everyone, and welcome to the live stream for today, December 4th. My name is Matthew. I am one of the behind the scenes staff here at Teach Astronomy and Astronomy State of the Art. Thank you for being with us today. We are excited. This is our second to the last live session before the holiday season, the winter holiday season begins. We have one more, and then we take a break. Um, so let me just welcome those of you who are with us, who are new, and those of you who are with us again. It's always great to be here with you. I'll go over the sort of the way that this works. Please post your questions in the chat. I will grab the questions from there. I see all of the questions, so you only need to ask your questions one time. Please don't spam with repeated questions. Make sure they're clear, that I know exactly what you're asking. So those were more likely to get chosen. If you just post facts and information, I don't know whether those are related to questions. So make sure your questions are clear. And I try to go in order that questions are asked, but I do jump around a bit to give a variety of participants a chance to have their question addressed and also to get a variety of topics. So that's kind of the mechanics of how these live sessions work. Chris, I will hand this over to you to welcome everyone. And if you have a topic to guide or begin a discussion today, we'll start with that.
Okay, welcome everyone to our live session for the MOOCs or however you might have found us. I wanted to start today by talking about news in space astronomy, and it's news that indicates the changing landscape of who's really investing in space astronomy. The United States has had serious problems within NASA, leadership problems, and budget problems. It's not clear what NASA's budget for the next fiscal year is going to be, but under the Trump administration's proposal, the space science part would have been cut by almost 50%, a devastating cut to NASA. Congressional committees at the moment seem to be holding the line on a flat budget for NASA, and it's not clear how that will shake down. But regardless, NASA's budget is under constraint, and in real terms, given inflation, it's actually declining more or less every year. NASA's budget is 2 times lower than it was in real terms 20 years ago as a percentage of GDP. So the news from across the pond in Europe is that the European Space Agency is investing in space astronomy. They've announced a 3-year, $25 billion augmentation to their budget, and it's going to enable some very exciting missions, and notably a new X-ray telescope called New Athena. And that's important because X-ray astronomy can only be done from space. And NASA had a flagship X-ray astronomy observatory, the Chandra Observatory, which has been operating for decades, not as long as Hubble Space Telescope, but close to it. A remarkable facility that's done incredible science, but it's expiring, and it has no successor. There's no current plan for an American-led X-ray astronomy satellite. There are proposals, there are ideas, concepts, but there's no indication in the next decade that anything will be launched. So New Athena would be the main game in town for X-ray astronomers worldwide. The Europeans are also planning an Enceladus mission. That's very exciting. Enceladus is a tiny moon of Jupiter, where we've seen icy geysers sprouting from the surface. Under the surface, it appears that there's liquid water under pressure, and there are very much the ingredients for life there. The jets were sampled by Cassini when it did flybys of Enceladus, and it has salty ingredients, and it has all the indications that it's a liquid body of water that could host microbial life. So the Europeans are going to actually do a lander, an Enceladus lander, which would really up the game and possibly detect life on Enceladus. This is all taking a long time. Its funding is secure, but it takes a long time to design, build, and send the mission out. So we're talking about a decade for that to happen. Meanwhile, there's some news or closer on the horizon after being stuck by having partnered with Russia on the Rosalind Franklin rover, the European rover mission to look for life on Mars. That went onto a hold with the Ukraine war. Europe has finally found a launch vehicle and is going to send the Rosalind Franklin rover to Mars. That's exciting because really for the first time, as good as the Perseverance and Curiosity rovers have been, they are not life detecting missions. They just do not have that kind of capability. The Rosalind Franklin rover does. It's named after Rosalind Franklin, who of course was the unsung heroine of the discovery by Watson and Crick of DNA in 1953. The Rosalind Franklin rover has a remarkable capability because apparently it can drill about 4 meters down under the Martian surface. That's exciting because the surface soil is sterilized by radiation, given the thin Martian atmosphere, so it's unlikely that life could survive on the surface. But underground, it's completely possible, sheltered from radiation, possibly with water kept liquid by pressure, possibly in an aquifer. So the Rosalind Franklin rover is a true life detection mission. And almost to rub salt in the wound of the straits of American space science budgets, the budget constraints on NASA are making it very unlikely now that the Mars sample return mission will go ahead. It's already had a fair amount of money spent, but the price tag's ballooned to over $11 billion. And meanwhile, the Chinese are offering to pick up in 2028 the 33 samples that the rovers have been stashing for eventually bringing back to the Earth. So if the Americans can't get their act together and provide the money to bring back the samples, the Chinese have offered to step in and bring back the samples, and they would share them with the international community. So that's a little update on the space astronomy game.
Excellent. Thank you much. Lots of stuff going on. The first question that we will start with. So, sorry, getting back to that. So, if anybody has any questions related to those topics that Professor Impey just discussed, put those in the chat, and we will come back to them. But now we'll get started with some of the questions that were there when we started the session. So, this first question for today is from Claw4156, who asks, "Hello, I'm wondering why sometimes astronomers can see a galaxy 13 billion light years from Earth, but then have trouble seeing something at the edge of the solar system? Thanks."
Yes, I mean, the visibility of objects in the universe just depends on their intrinsic size and their composition, and also whether they emit light. Distant galaxies that are being found are being found with incredibly sensitive telescopes, the Hubble Space Telescope and mostly now the James Webb Space Telescope. So 6.5 meters in space, working in the infrared. But galaxies seen at that distance are extraordinarily luminous objects. They are, to compare to the Milky Way, they're probably tens or hundreds of times more luminous than the Milky Way. So these are extremely bright star-forming galaxies seen early in the history of the universe, and that's why they're visible. As for why objects at the edge of the solar system might be less visible or seem less visible, it's because they don't emit their own light. So any remote object, like in the Oort cloud, a comet that might be billions of miles from the Earth, these are objects that are maybe 5 or 10 kilometers across, so very small space rocks. And they're so far from the sun that they have almost no reflected light from the sun. And so they're extremely dim, and that's essentially why outer solar system objects are so hard to detect.
Excellent. Thank you very much. The next question is from one of our live participants. Adrian asks, Professor Impey, when did dust form in the universe? Did dust exist in the universe at the time only population 3 stars existed?
So it's an interesting question. Dust is an important component of the universe. The universe consists of stars that are aggregated into galaxies, but the space between stars does not just contain gas, mostly hydrogen and helium, but it also contains dust. So what is dust? As viewed up close within the solar system, where we can scrutinize the composition and even have samples that come to Earth, dust is mostly of 2 kinds. It's either silicate material, and that's essentially just what rocks are made of on the Earth. So these are tiny dust grains that are just like rocky dust grains. They are very small. The dust in interstellar space is much smaller than the head of a pin. It's maybe 100 microns across, these little dust grains. So many of them are made of silicates, rocky material, And some of them are made of just pure soot. They're just essentially carbon, charcoal. And so that form of dust is also seen in space. When it was formed, well, because carbon and silicon have to be produced by stars and ejected, there couldn't have been dust in the universe before the first generations of stars. So there had to be generations of stars generating heavy elements by fusion, ejecting them into space before you can have any dust at all. And then, of course, it doesn't take too many generations of stars to create enough carbon and silicon and other ingredients, oxygen, for example, to make dust particles. And so those dust particles have been around for billions of years, and they're part of the formation of every solar system. They also form a thin haze or gauze that obscures our view of objects because they scatter and absorb in optical radiation very efficiently, whereas infrared radiation goes straight through. For example, we cannot see to the center of our galaxy, less than 30,000 light years away, in visible light because there's so much dust along that path, whereas in the infrared we can see the center of our galaxy. So dust is important because in our galaxy and beyond, it obscures our vision of distant objects.
The next question is from Monty Roeder, who asks, aside from the money issues, why does it seem that it is harder to get back to the moon now than it was decades ago?
It's a good question. I think it seems hard to go back to the moon. The last time anyone set foot on the moon was 1972, Apollo 17, sorry. And it's been over half a century. That's amazing. And it's not that far away, compared to Mars, for example. Why it's hard to go to the moon is simply the expense and also the motivation. What is the reason to go to the moon? We need a compelling reason to go there because it is expensive. It is difficult. On the first circumstance of the Apollo missions, it was a matter of American national pride, a competition with the Russians, something that had never been done before, humans standing on another world. I mean, it was pioneering in that sense. And once you've been, the pioneering aspect sort of goes away. However, it is likely that within a decade or more, even though the Artemis missions are still to come, and it seems like it's taking us a very long time to go back to the moon, there probably will be a lunar economy because eventually enough corporate entities and governments are interested in mining on the moon, in finding resources and shipping them back to the Earth, or in establishing a toehold and a base and a projection of their national power, that the moon will need infrastructure to support all those activities. And so there are various entities, private and public, that are preparing for what eventually will be a lunar economy.
The next question is from Wendy Traver, who sent an email. If gamma rays and other forms of light have different energies, how can they travel at the same speed?
So the nature of electromagnetic radiation, which was determined and theorized by James Clerk Maxwell in the late 19th century, is that electromagnetic waves travel in a vacuum at 300,000 kilometers per second. That's the speed of light. And the only variation is in their frequency or their wavelength. So all forms of electromagnetic radiation are the same fundamental phenomena. They're coupled, oscillating electric and magnetic fields. They all propagate at the same speed, and there's an inverse relationship between wavelength and frequency. So in that spectrum of radiations, the shortest wavelengths go with the highest frequencies, and therefore also the highest energies, like X-rays and gamma rays, whereas the longest wavelengths go together with the lowest frequencies and the lowest energies, and that would be radio waves or microwaves. But fundamentally, it's all one type of physical phenomenon.
The next question is from Magyari Paul Stefan, who asks, good evening. If one is looking far away in space, they see it as it was in the past because of distance. Does that not mean that the universe is slowing down instead of speeding up?
No, the concept you're talking about is look back time, and that is a fundamental feature of the universe. It just relates to the fact that old light, distant light is old light, that it takes the The universe is large, speed of light is also very large, and that means it takes a finite time for light to reach us from distant object. For within the solar system, that time is only hours. To the nearest stars, it may be decades, and to the galaxies beyond us, it's millions of years. So it has nothing to do with the expansion of the universe or whether it's increasing or decreasing. It's simply a fact of the size of the universe and the finite speed of light, which means that it takes time for light to reach us. So the further out we look, the further back in time we look, and that's the concept of look-back time.
The next question is from Bharati Yash, who asks, what's the current update or current status of the 3I Atlas comet? Can you talk a little bit about the background and if there has been any updates on our knowledge of it?
Right. The 3I Atlas is an interstellar comet. It's a comet that originated in another star system, and it's unusual because it numbered three. There have only been three of them. There was Oumuamua and Borisov are the other two. And Oumuamua was heavily studied, of course, and in the news a few years ago. There's been a controversy with Atlas, as there was with Oumuamua. A few people, notably Avi Loeb at Harvard, saying that it's an interstellar artifact, that it's an alien artifact, because it has properties that resist explanation as an interstellar rock and ice ball. But the scientific community has pretty much studied it carefully. You only get some time to study it before it whizzes through and never comes back again. So there's only ever been a few weeks to study 3I Atlas, and it has some puzzling features, but nothing that would fundamentally indicate that it isn't rock and gas ball where some of the gas has been activated by proximity to the sun.
The next question is from, again, one of our live participants. Interalia 300 asks, hello, Professor. Is there any merit to the theories that dark energy is generated by primordial black holes?
This is an idea that's been in the theoretical literature recently and in the last year or so. People are still casting around for a physical understanding of dark energy because we essentially have none. We have a operational understanding of dark energy in terms of it's causing the accelerating expansion of the universe. The space-time expands faster and faster and carries away objects faster and faster. That's what we see. That's what we know. The physics behind it is very unclear. Primordial black holes could conceivably, as they evaporate, as they radiate their Hawking radiation and then evaporate, which is a prediction of Stephen Hawking, that force could act in some way similarly to dark energy. The trouble is that the primordial black hole, the window on primordial black holes in terms of detecting them have almost been closed shut. People have been looking for primordial black holes for a long time. And a reminder that a primordial black hole is a black hole formed not from a dead star, collapsing massive star, but early in the universe from the highly dense, highly curved space-time in the early universe, which could generate microscopic black holes, really small ones. And they will still persist, but eventually they will evaporate and release radiation and energy. There's no evidence for primordial black holes. That's the way things stand at the moment. So speculation about them being associated with dark energy is sort of really two levels of speculation.
The next question is from an email. Hernan Reyes asks, if and when we do find a habitable planet combined with bio and even techno-signatures of a technologically intelligent signal, how would we be able to communicate with whoever's there? How would we establish some minimum form of dialogue when we can't really even communicate with other intelligent species on our planet, like dolphins or octopi?
Yes, this is a serious issue. If intelligent species, civilizations do exist beyond the Earth, the communication issue becomes paramount. And it's a good point. We can't communicate with creatures with whom we share, say, 98% of our DNA, chimpanzees, let alone an alien of unknown function and form. So people don't really know how to do it. The key is you have to look for a signal that you think is artificial and can't be produced naturally. And then you at least can assume that you're dealing with some alien intelligence. And the premise of SETI, the Search for Extraterrestrial Intelligence, is to look for artificial signals, pulsed information that you can somehow decode. But whether you realistically can decode information from an alien civilization is highly uncertain. And most scientists think it's unlikely that communication really is a viable option. On Earth, communication is culturally locust beyond with other species where it's impossible for the most part. So the cultural context of an alien civilization is so unknown that there's no basis for understanding how communication might occur. So I agree, it's a cipher. It's a really big problem. Of course, finding an artificial signal in the first place would be the exciting part, because that would indicate at least that there's someone that we could potentially talk to.
As a kind of follow-up question to that is, would sending out a list of prime numbers, as was done towards Earth in the film Contact, make sense in your view? And what would be the purpose of something like that?
So the idea of beaming out, either listening for prime numbers being pulsed in as a signal or sending out pulsed signals that represent the prime number sequence, it's not a bad idea, because the concept here is that mathematics is universal, that math applies everywhere in the universe, not just on Earth, and that the laws of physics, for example, have a mathematical basis, whereas all the stuff we deal with in communication and human language is highly dependent on culture. We have no idea about culture beyond Earth. So prime numbers is not a bad idea. Communicating through math or perhaps logic would be a good idea. And indeed, that's famously became a part of the book Contact by Carl Sagan, and then eventually the movie based on that book, where in a famous scene in that movie, Jodie Foster is sitting in the control room at the Very Large Array in New Mexico, so the real place they filmed on site. And as they're looking at their star system, they see this series of pulses, and they gradually realize 1, 2, 3, 5, 7, 11. These are prime numbers. That has to be artificial. That has to be an intelligent civilization. So it's not a bad premise. Of course, you could criticize it by saying, well, it doesn't really convey anything interesting. I mean, for a civilization to tell you that they understand prime numbers as we understand them, you can't do anything with that. You'd learn nothing else about the civilization with that level of communication.
Excellent. Thank you very much for that answer. The next question is from Lawrence K. Hi, Professor. Regarding dark energy, as space expands, is dark energy created, or is it simply a part of the expanding space-time landscape?
That's a good question. It sounds like semantics, but it actually has a physical meaning, that question. The best way that we could understand it is that dark energy is actually created in the expanding space-time manifold. We use the term manifold to refer to a mathematical surface because space-time has a geometric structure according to general relativity. So yes, dark energy is created in the expanding space between galaxies, and so there's more of it, and that creates more negative pressure, which drives the galaxies further apart and the space-time to expand ever faster. Where does that energy come from, given that we have a law of conservation of energy? Well, energy can be borrowed from the vacuum of space and can manifest in the vacuum of space. That's well-known lab physics. So it's not implausible that it can happen on a cosmological scale. But as I said, the physical basis for dark energy at the moment is completely unknown.
The next question is from Sebastian, who's on with us live. If the excess of gamma rays at the center of the Milky Way really does come from dark matter annihilation, how would our models of galaxy formation and structure change?
Yeah, that's an interesting point. First of all, it's referring to the fact that gamma ray telescopes have seen an excess of gamma rays near the center of our galaxy, not at the very center, but distributed near the center of our galaxy. Why is that interesting? Because gamma rays generally in the galaxy will only come from supernova remnants or very high energy stellar remnants. And so to see a concentration of gamma rays in the center of our galaxy, which is sort of where most of the matter and the dark matter is, might implicate the gamma rays with dark matter. And there are theories of dark matter where dark matter annihilation can occur and lead to gamma rays. However, that's not a unique explanation for the gamma rays from the Milky Way. It's not ruled out that there are sufficient stellar, high-energy stellar remnants, which would also concentrate by gravity towards the center of our galaxies, to explain this radiation, because it's quite a weak signal.
The next question is from a live participant. Faisal asks, many researchers are talking about colonizing Mars. Is it possible to create a normal life cycle on Mars like the one on Earth?
Since humans on Mars will be having to live in a very artificial environment, it is indeed possible to create a normal human life cycle. The Martian day is slightly longer than the human day, so if you were in a translucent habitat or a dome, which is unlikely, the domes are likely to be battle hardened against radiation and so opaque. So really you're immune from the natural Martian day, and you can live a normal diurnal cycle of human life. And so I think for comfort and psychological comfort overall, humans are going to try and mimic their terrestrial environment as much as possible. And in a very controlled space of a Martian habitat, that would be possible.
The next question is from David Gold, who asks, why is a standard moon halo at a 22-degree angle? Why does that seem to be kind of a universal?
This is also related to the geometry of rainbows and sundogs, moon halos, all of these phenomena, these upper atmospheric phenomena, which are based on light, reflected light from the moon, of course, coming in through the atmosphere, and then being refracted or bent by tiny ice particles in the upper atmosphere, the sort of cirrus layer. And the geometry of that internal reflection in an ice particle is such that the preferred angle is about 22 degrees. And so mapping that around the moon, you end up with a circular symmetry where you have a halo of that size. And a rainbow, of course, has the same angle, but it's only a hemisphere. And with sundogs, you have little outriggers to the sun, which are also 22 degrees away from the sun on either side, reflecting where most of the light is coming from. So all of these are sort of similar phenomena, which reflect light coming through the atmosphere and then refracting through tiny ice crystals in the upper atmosphere.
The next question is from David McKenzie, who sent an email. Are scientists working on any projects related to the control or manipulation of gravity? And would this even be a viable activity?
Well, it's long been a dream in science fiction and even in real science to somehow control gravity or master gravity or create an anti-gravity device, which at the moment is pure science fiction and against the laws of physics. So the simple answer to the question is no. There's been never been any success in modifying the force of gravity. Of course, you can create situations of buoyancy on the Earth, not just in orbit around the Earth in zero gravity, where you can offset the force of gravity by other forces, electrical, magnetic forces, hydrostatic forces, and so on. So you can essentially cancel gravity in particular circumstances, but none of that amounts to manipulating gravity itself, which nobody's successfully done.
The next question is from Sumaya Bhala, who asks, hello, Professor. Are population 3 stars still purely theoretical, or do current observations suggest indirect evidence of them?
This is a hot field in astronomy research, especially with the James Webb Space Telescope, which was built essentially to detect, its killer app, if you like, was to detect first light in the universe, which is a population 3 star. So the population 3 stars are predicted theoretically. It's assumed that before galaxies gather, the first amount of collapse of gas clouds into stars would generate stars with no elements beyond hydrogen and helium, the primordial elements, and those are population 3 stars. the theory suggests that very massive stars can form this way, up to 200 or even more times the mass of the sun. They would die catastrophically as supernova, leaving behind black holes, quite significant black holes. This has not been observed. So there are various indirect observations, and they bubble up in the press and the literature every few months, that population 3 stars have been detected, but there's been no unequivocal evidence of them yet. However, James Webb has probably a dozen ongoing projects designed in different ways to look for them.
The next question is from Meadow Focus, who asks, what is your take on the UAP disclosures in Congress in relation to astronomy?
So UAP stands for Unidentified Aerial Phenomena, and it was essentially a rebranding of the term UFO by the U.S. military to try and avoid the stigma of UFOs over the decades, where they're bound up in conspiracy theories and clearly non-scientific types of evidence. So the military wanted to sort of cleanse that stigma, and they invented this new acronym, but it's essentially a UFO. And because of the reports from Navy pilots and various other military observers, the military was motivated, for national security reasons, to start collecting evidence of UAPs, the data. And a congressional committee was formed, and a scientific advisory committee was constituted, which includes prominent astrophysicists, I know a number of them, to study the UAP reports. I think there are now well over 1,000 UAP reports from the last 5 or 6 years. And the first report of the panel and the committee to study them, looking at probably 500 or 600, I think, found that there was no evidence of extraterrestrial aliens visiting the Earth. They could explain most of the UAP sightings in a conventional way, and some small fraction, maybe 4 or 5%, were unexplained. But that, in and of itself, did not mean you jump to the conclusion that it's aliens visiting. So this is all active and ongoing, and I think the number of UAP reports is just, they're going to be continue to accumulate. The scientists will investigate as many as they can and categorize them into conventional explanations, and then maybe this more interesting subset where they don't know what the explanation is.
So the next question, and I will just preface by saying that there are no active candidates right now, because we are not currently in a political cycle in the United States. But Yang asks, is any presidential candidate promising for the sake of space policies? Since we talked about that early in the way that policy is affecting astronomy, we can sort of address something about that.
Say it again. Is any candidate
is any presidential candidate promising for the sake of space policies?
I see. So the general statement that can be made about what presidential candidates in any election cycle say about space policy is it's quite limited. It is not in the top tier of issues that most presidential candidates talk about. They're typically going to talk, as we've seen in recent cycles, about the economy fundamentally. They're going to talk about national security. They're going to talk about immigration. They're going to talk about healthcare. They're going to talk about the things that everyday people care about, and then some things they don't care about as much. And to be honest, space and science really don't figure in that top tier. So it's unusual, and some presidential candidates in previous cycles have not even had a policy platform on space science or astronomy, which is a shame. So it's very hard to tell what's going to happen in the next cycle, but I think history will repeat itself where space and astronomy don't really figure heavily into the policy pronouncements of the candidates.
The next question is from Arif Roni, who asks, the Australian Space Agency recently made a new thin or ultra thin solar panel, solar cell as part of the Moon to Mars program with NASA. I mean, can you talk a little bit about the benefits of solar cell technology, and how does radiation affect space solar panels differently than on Earth?
So the Australians are doing what you have to do when you deal with space astronomy, and you have to minimize weight. So whatever you send into space and solar panels are a critical element of space operations because you have to get energy from somewhere, and the sun is the place to get your energy. So it's very promising to develop ultra-thin solar panels for space applications. So that's a good thing. There is a downside, though, to operating in the space environment. On the upside, there's no obscuring atmosphere on a solar panel on the Earth. The light has to go through the Earth's atmosphere, where it's attenuated, where some wavelengths get through and some don't. So you're only getting a fraction of the true solar energy that hits the top of the atmosphere. When you're in space, you get the full solar energy, but unfortunately, you get a lot of high energy radiation. You're exposed to cosmic rays, you're exposed to microscopic dust particles, and the very high energy tail of the radiation can be damaging to the solar panel material and detector. The tiny dust particles moving at thousands of miles an hour cause tiny pits in any solar array material, and so they will degrade it over time. And we've seen with space astronomy, with the solar panels for the Hubble Space Telescope, for example, that have been out there for decades, that these materials do degrade in the space environment over time. They do not last forever and have to be replaced.
The next question is from, excuse me, one of our live participants. How confident are we that we are in a universe represented by a lambda CDM, so a cold dark matter universe, and what challenges that assumption the most?
Yes, the standard paradigm of cosmology is and has been for several decades, 3 decades basically, since the discovery of the accelerating universe, has been what's called lambda CDM. The lambda in that refers to Einstein's cosmological constant, and that's essentially a reference to the dark energy that's accelerating the expansion. And then the CDM refers to cold dark matter, which is our best guess as to the nature of the dark matter that is ubiquitous and weighs 5 or 6 times more than all the normal stars and in galaxies. The cold part of cold dark matter refers to the physical properties of the assumed particle, where it was subrelativistic at the time the universe formed stable atoms. The lambda CDM model has had extraordinary successes. When matched to the best microwave satellite data from the cosmic microwave background of exquisite precision, it fits the data exceptionally well. And so astronomers gain confidence over these last few decades as more and more space missions gather more and more data, more galaxy surveys accumulate millions of galaxy redshifts, that the CDM, lambda CDM, fits pretty well. So that's the good news. The bad news is that it's not perfect. The bad news is, of course, that we don't understand what dark energy and dark matter are. So it's a black box at some level. We're building a model with the 2 primary ingredients that we don't physically understand. And then the second problem is that there are issues like the Hubble tension, which is a whole different topic. There are issues where the lambda CDM model doesn't fit, or where there are inconsistencies in matching different data sets. And people are really undecided at the moment whether these inconsistencies are just based on different measurement techniques, where people have to do better, gather more data, reconcile the differences, or whether they're fundamental and they will bring down the model. At the moment, we don't know the answer to that question.
The next question is from one of our live participants. This year was celebrated as, and let's see what it was, the International Year of Quantum Science and Technology. And the Nobel Prize in Physics was also given in this area. So I guess the question is, what are your thoughts on such a profound celebration? And I guess, so what are your thoughts on, this kind of big international year of quantum physics, but also how do you evaluate these kinds of discoveries for a Nobel Prize?
I think it was a well-awarded Nobel Prize. Nobel Prizes sometimes are given in physics to quite recent discoveries. This is given for theorizing that has been in place for quite a while, so it's quite mature quantum physics. We're also in 1925 almost marking a centenary of some of the development of the foundations of the quantum theory. So this is a very mature theory, a very successful theory. And as we hit the 100th anniversary of quantum theory being developed for the first time, we're seeing brand new applications. Already quantum theory is built into our lives in a profound way. Your smartphone could not function without quantum mechanics operating at the substrate level of the detector. But we're now moving towards quantum computing, which is still in the lab, in the research lab, not in the commercial realm, but probably will be in a few years. We're also working on understanding entanglement and some of the sort of philosophical underpinnings of quantum theory. So for a mature theory, 100 years old, it's still very active at the research level.
Excellent. Thank you very much. The next question is from an email question. Using parallax calculations to calculate the distance to planets and even stars close by, I understand. But how do you calculate the distance to stars or nebulae 1,000 or more light years away? Surely the parallax method doesn't work for those distances, or does it?
Right. So parallax is a method that's a very direct trigonometric method for measuring distance. It's essentially you define a little triangle based on the Earth's orbit of the sun. From one, as a star seen from one side of the Earth's orbit to the other defines a skinny little triangle. And if you measure the apex angle and you know the distance from the Earth to the sun, then you've determined the geometry and you can measure the distance. And this is a very profound technique. Of course, it worked for the first time in 1840s to measure the parallax of the first star, how we knew how far away the stars were. Since then, it's been used reliably to distances of a few hundred light years, and with the Gaia satellite, even to distances of a few thousand light years. But that's still a small fraction of the galaxy. So when you go beyond, say, a few thousand light years, where the angles of a parallax measurement are just too small to reliably measure, so you can't use trigonometry, then you have to use more intrinsic properties of stars. You have to treat stars or find special types of stars or stellar remnants that are acting like standard light bulbs, so a fixed luminosity, where their apparent brightness will give you their distance. So when you go beyond parallax, you have to transition to fundamentally different distance measurements.
The next question is from Eduardor, who asks, a very old galaxy similar to the Milky Way has recently been found. What are the consequences of this discovery?
I think it's expected that there will be galaxies like the Milky Way found at large distances and look-back times, but not beyond a certain point. And these galaxies should not be identical to the Milky Way. The Milky Way is a mature galaxy. It formed many of its stars, especially in the bulge and the halo, billions of years ago, and is still forming stars in the disk, although it's rapidly exhausting its gas. An early version of the Milky Way has far more fuel for building stars, and so it's expected to be much brighter and more luminous. So it would be very unusual to find a true twin of the Milky Way galaxy 13 billion years ago, because galaxy formation was somewhat of a different process. It was more vigorous. The universe was hotter and denser. Stars were forming at a much more rapid rate. So when we say we found a twin of the Milky Way, it's not a literal twin.
The next question is from one of our live participants. Heavy Kev asks, if all the galaxies are moving away from each other, why is our galaxy predicted to collide with Andromeda?
So the overall cosmic expansion has galaxies all moving away from each other. But if any pair of galaxies are close enough together, their mutual gravity can overcome the cosmic expansion. And that's what's happened in the case of the Milky Way and M31. So within the local group of galaxies, where M31 and the Milky Way are the two largest, and then there's a few dozen dwarfs, the Milky Way and Andromeda, Milky Way and Andromeda distance 2.25 million light years, is such that for galaxies of that mass, trillion times the mass of the sun, that's enough gravity pull to exempt them from the cosmic expansion. And so they're moving towards each other at 100 kilometers per second. And we see other examples of this in the nearby universe. The overall cosmic expansion still holds, but on smaller scales of galaxy-galaxy scales, like a million light years, you can definitely have galaxies that are moving towards each other or bound to each other or orbiting each other. That's not unusual at all.
The next question is from an email. Wendy asks, Can you please explain the difference between particle horizons and event horizons?
So an event horizon is a consequence of a black hole. Anytime you form something that fits the definition of a black hole, it has an event horizon which is defined by its size, a scale called the Schwarzschild radius, named after Carl Schwarzschild, a theorist from the early 20th century and a famous cosmologist. So that's the event horizon, and it's an information barrier. It defines the limit of information from the object because no light can escape from within the event horizon. The particle horizon is a different concept. It's based in cosmology, and it essentially relates to the distance looking out in space in an expanding universe from which no information can have reached us within the age of the universe, pretty well known to be 13.8 billion years. And so there's a limit to our information of the distant universe caused by the particle horizon, but it's rather different conceptually from a static black hole event horizon, because the particle horizon in cosmology is continuously changing as the universe expands.
The next question is kind of a personal question about how someone can transition. So Illusion Eyes asked, as a computer science engineer, how can I transition my research to astronomy and astrophysics?
Well, computer science has moved over the years and decades to become quite central in modern astrophysics because modern astronomy, both the observational aspect and the theoretical aspect, depend heavily on computers and on coding and on computer science and simulations and running models of things. So if you have a computer science skill set, you're very well situated to make the transition into an astrophysics environment. You might initially not be able to be fully integrated into an astrophysics group without getting some astrophysics knowledge. Otherwise, you're just going to be like a hired coder or something like that. But it certainly does offer a path, and there are examples, and I know some of them, of people who've had a computer science background, have a strong interest in astronomy, have learned the astrophysics or taken master's degrees or courses at that level, and then have moved into a world where they can use their computer science skill to solve fundamental problems in astrophysics. So it's certainly a viable option.
The next question is from one of our live participants. Why and when should someone learn about Hamiltonian mechanics?
It's a physics concept, a sort of operator that relates to how forces apply in the universe and how you calculate dynamical situations in physics. It's typically a graduate level mechanism. It typically comes up in graduate level astronomy courses with the same fundamental mathematics. You need differential equations under your belt, and you need calculus under your belt to be able to talk about Hamiltonians. But these are sort of foundational tools of modern astrophysics.
Excellent. Thank you very much. The next question is also from one of our live participants. Um, can it be possible, or is it possible for the moons of Mars to also be places where we could find evidence of life?
So Mars has two small potato-shaped moons, Phobos and Deimos. They're irregular in shape because they're not large enough for gravity to have made them round. And their size, their very small size, makes them very unlikely targets for astrobiology. And that's because they almost certainly do not host liquid water. The only places we've seen with liquid water are planet-sized objects or large moons like Europa. The smallest example would be Enceladus, but Phobos and Deimos are not kept hot in the same way that Enceladus is in the grip of a giant planet. So for various reasons, mostly to do with their small size and their exposure to intense UV radiation, they're unlikely astrobiological targets.
The next question is from one of our live participants. Eliezer Santos asks, what are the chances of, so the question is there any news about the discovery of a large planet in the solar system? And then more generally, what are the chances that we will someday discover another large planet in our solar system?
The odds of discovering a new planet in our solar system, especially a large one, are very low, almost zero. And that's just because we understand, first of all, the solar system is not that large, a few billion miles across, and we have very sensitive telescopes looking throughout the solar system for decades. So if there were a large planet there, it would reflect enough sun's light that it's not that dim, and we would see it. Remember, 5 planets are naked eye objects, so they're pretty bright. So even if it was in the outer solar system, it would be easily detectable by the telescopes we have in operation. And then the second reason is a physics type reason, which is based on the orbits of the planets that we measure quite accurately. And if there were an unseen dark giant planet somewhere in the solar system, it would perturb the orbits of the planets we know about in a way that we simply don't observe. The planet orbits do have small residual irregularities, but they're tiny, and so we can almost rule out just from the planet's orbits themselves that there are no hidden planets out there.
The next question is from an email. Why is iron the most stable element when the strong force is stronger in smaller nuclei?
The reason that iron ends up being the most stable element, and the physicist's way of looking at this, is in terms of the binding energy per nucleon. A nucleon is a proton or a neutron. So these are the nuclear particles in the atomic nucleus. And so the binding energy per nucleon goes through a minimum at iron. And that means it's the most stable element. That means that no energy is obtained by trying to fuse beyond iron. Now, the reason for this is a sort of geometric reason in a sense. The number of nucleons in iron, in an iron nucleus, is such that they pack into a very minimum energy configuration, and that means it's very stable and fairly robust. If you go beyond that, the imbalance in the number of neutrons and protons gets larger. There's a larger excess of neutrons over protons, and that eventually leads to radioactivity. And if you go to lower mass elements, there isn't an imbalance of neutrons and protons, but the overall binding energy changes significantly, making them less stable.
We have another email question. How would gravitational evidence suggest or indicate a global saltwater ocean on Enceladus, separate from Cassini analyzing the plumes?
So gravitometric measurements are very important. So basically what that means is you're essentially measuring the mass distribution by the gravitational effect. And you can map an object if you have an orbiting satellite with a gravitometer. You have to have an instrument that's built to measure the gravitational effect. You can map it, and rock and water, for example, have quite different densities. You can't probably distinguish the difference between a salty water and a water without salt. That's too subtle. But certainly you can look for evidence of subsurface oceans that you might not see with your direct imaging. And the gravitometric measurement will not only tell you that they exist, but also tell you roughly how big they are.
The next question is from David Gold, who's on with us live. Is a unified field theory needed before dark matter and dark energy can be fully understood?
Not necessarily. Dark matter can be understood if we can detect the fundamental subatomic particle we believe is responsible for dark matter. And there are lab and deep mind experiments ongoing, maybe over a dozen worldwide, which are hoping to detect that fundamental particle. And that we can find that particle and understand its properties experimentally without a unified field theory. Dark energy is trickier because we don't understand the nature of dark energy. So it's a little harder to answer that question, especially since dark energy does appear to be a property of the vacuum and a property of expanding space-time. It may well be that we can't make progress in dark energy until we've had some way to unify the theories of general relativity and quantum theory.
The next question is from one of our live participants. In climate science, there is a feedback loop that relates that is related to various factors of radiation, carbon dioxide, water vapor. Is this feedback loop considered or considerable in other planets in space?
Yes, it probably will be. Earth's climate is subject to a number of feedback cycles. Some of them are positive feedback, where the effect reinforces itself and leads to a runaway. Greenhouse warming and greenhouse gas is the best example of that. And some of them are negative or stabilizing, where they act almost thermostatically to regulate the temperature. So the Earth's climate has examples of both kinds of feedback: a positive feedback that would cause temperature to continue to rise at an accelerating rate, and a negative feedback that would stabilize the temperature. We imagine such mechanisms will operate on planets elsewhere, especially Earth-like or terrestrial planets. The trouble is, we simply don't have any kind of detailed information about the atmospheres of Earth-like planets elsewhere. We're just beginning to learn what those atmospheres are made of by biomarkers and observations with James Webb and eventually ground-based telescopes. But our understanding of exoplanet atmospheres is far too primitive to measure such feedback effects operating. But we could speculate theoretically that they should operate.
All right, we have to wrap up. So we'll take one final question and then we will be done for today. The final question is from an email. What is a dimensionless constant? Can you give an example of one, why it's dimensionless, and what's the significance?
It's dimensionless constant is one that doesn't have one of the fundamental units of mass, length, and time. So all physical quantities are parsed in terms of these fundamental properties. A dimensionless constant is one where the way you combine your physical quantities leads to no dimensions. In other words, the dimensions of mass, length, and time just cancel out, leaving you with no physical dimensions. The fine structure constant is probably the best example of that. That's a number, a pure number, very close to 1 divided by 137, and it takes the strength of the weak nuclear force. And in terms of the physics, the way you combine the parameters, you end up with this dimensionless number. So it's one of the very few dimensionless numbers in fundamental physics. Thanks for a good range of questions today, as always, and we'll be back with you in a couple of weeks. We have one more scheduled. Matthew can tell us when it is.
Yep, no problem. The next one is in 2 weeks. It is December 18th, so it's going to be another Thursday. So we will see you all at that date and same time as it was today. So make sure you put that on your calendar. Thank you all so much for joining us today. If you haven't checked out our online classes, scroll back to the top of the chat and there's a link to the Coursera courses. And so you can feel free to check those out. We have 3 active courses. And if you haven't had a chance to check them out, they're a fantastic way to get into and have an introduction to the basics of astronomy, astrobiology, and the history and philosophy of astronomy. So again, thank you all for joining us, and we will see you all again in 2 weeks. Take care, everyone.